This video gives a brief introduction to dynamic FEA, specifically doing transient or time-dependent analysis using the implicit methodology. It wraps up with an example working through the process for a single degree of freedom model. Let's start out with a quick overview of transient analysis. What we're trying to do is solve this equation shown for a single degree of freedom, m d double dot plus c d dot plus k d is equal to f. So we have a mass times an acceleration plus damping times an velocity plus our regular stiffness matrix times our displacements is equal to a forcing vector, or a force in this case. So transient analysis, the goal is to use information at the current and prior times in order to predict what's going to happen next, like reality. So imagine that we've got some displacement as a function of time, and we don't know what that curve looks like initially. What we're trying to do is produce this curve, or at least identify points on this curve, using finite element analysis. So for example, we know that at time tn we have some displacement. And we know also what we did previously. So we know the displacement at a prior time. Our goal is to use this information to predict what's going to happen at the next time. And we're going to be talking about time steps. So we've got these delta t's shown. We're going to have potentially varying delta t, but for the moment we'll assume it's constant. And then we jump from one time to the next time. So I'm going to be referring to time in terms of indices, time 1, times 2, times 3, and so on, where the index is a multiplier on the delta t. So 3 delta t would be the time corresponding to time step 3. There are basically two ways to perform transient or time-dependent analysis in FEA: implicit versus explicit. In implicit, the degree of freedom vector is buried, or rather multiplied by, a stiffness matrix, and then it's equal to something like a forcing function on the other side. That means in order to solve for degrees of freedom, we still need to do something like a matrix inversion, similar to what we do for static analysis. Explicit is something sort of fundamentally different. The degree of freedom vector is not multiplied by a stiffness matrix anymore, which means that we don't need to invert the stiffness matrix in order to project what's going to happen at the next time step. That makes explicit much faster for any given time step, but that's not all there is. So the implicit method is based on Euler time integration. That's to estimate the current time step based on what's happened in the prior time step. Explicit, on the other hand, is based on the central difference method for approximating. That's going to estimate your time derivatives. And I'll go into both of these in more detail in this and the next video. The implicit method is stable for all delta t. So you can go to a very large time step and it won't explode on you. However, it will become inaccurate. So just like with FEA, the size of the delta t matters in terms of your accuracy. For explicit, the analysis will actually blow up if you go beyond a very small time step, but as long as it doesn't blow up, you can be confident that it is accurate. The time step required for explicit to not blow up is much smaller than the time step required for implicit to be accurate. That means implicit is best for your long duration events. If you're going to be running over a considerable amount of time, which in FEA terms might just be a matter of seconds, could be a long period of time. Explicit is best for very short duration events, things like impacts. For the rest of this video, I'm going to focus on the implicit time integration. So again, we're solving this md double dot plus c dot plus kd is equal to f. And another term for implicit time integration is called the Newmark's method. The basic idea is you're going to start out by writing that equation of motion for the next time step. Wherever you are, you want to be projecting forward to the next one. So assuming you're at n, we're trying to see what happens at n plus 1 time step. But then we're going to take the speed and the acceleration terms, so that's the dn plus 1 double dot and the dn plus 1 dot. We're defining those using information from the current time step, so the n time step, but also the n minus 1 time step. Now we're going to treat these as known quantities because, in fact, they are known. We know them from the current and the prior time step. We move them over to the right-hand side because they are known quantities, and in FEA we like our known quantities to be on the right-hand side and our unknowns on the left-hand side. Now once we do this, we can basically say we have a new system of equations. We've got a k bar, a new k stiffness matrix, times a degree of freedom vector for our next time step, and that's going to be equal to some effective forcing function in the n+1 time step. So in order to do this method, obviously we need to define speed and acceleration. And the approach we use are the Euler formulas, which you're familiar with from high school physics. The Euler formula says that the position at any time t can be calculated based on the current position, x0, plus the velocity times time, plus 1/2 at squared. And then similarly, the velocity at some future time can be calculated from v0 plus at. So if we write these in the terminology I'm using here with degrees of freedom, so that means dn+1, so the displacement at my n+1 time is equal to dn, my displacement right now, plus delta t times dn dot, so delta t times the speed at my current time, plus 1/2 delta t squared times dn double dot, so that's my acceleration at my current time. Similarly, we have an equation like that for the speed. But this assumes that acceleration is constant, or at least that your time step is small enough that it doesn't matter. But that won't necessarily be the case. What if the acceleration is changing over time? If the acceleration is changing, we can take advantage of the current time, but also information we don't yet know about the next time. That sounds a little bit odd, but I'll show you how it works. We want to use the current and the next time. So what we're doing is the first couple of terms here are the same, but now I'm introducing a term beta, which is going to allow me to tweak the relationship between how much of my current time matters and how much of my future time matters. And we'll introduce a gamma term in the speed equation for the same function. It's going to tweak that. So you can see in this case that if I set beta equal to 1/4, then I'm actually taking the average of my current and my future acceleration in my displacement equation. And if gamma is equal to 1/2, then I'm taking the average acceleration in my speed equation. And this is a typical assumption, but the nice thing about leaving them in as variables is for certain types of analysis or certain types of situations that you're analyzing, you might want to vary these a little bit. So it gives us the option to do that. What we want to do now is use that first equation to find the acceleration at the n+1 time. And this is kind of the cool thing. So we've introduced the acceleration in order to define our next displacement term. But now we're going to rearrange the equation to give us the acceleration at the n+1. So first off, I'm going to take the current displacement and the speed term, move them over to the left-hand side, and take the delta t squared times 1/2 and spread that into the terms on the right side, and then rearrange them one more step so I get dn+1 double dot as this expression. So now we can see the acceleration at the next time step is defined in terms of the displacement at the next time step, the displacement at the current time step, the speed at the current time step, and finally the acceleration at the current time step. The second equation from up there, the speed one, gives us speed at n+1. So the dn+1 dot, what we take is the acceleration that we just derived and we plug that in for the next acceleration term. Then we multiply things or expand things out and we have this expression for the speed at our next time step. So these are the two critical equations. We need to go back into the equation of motion and write the dn+1 the acceleration at n+1 time and the speed at n+1 time in terms of things that we know. So that's going to be the next step. So now I have my equation of motion for my next time step n+1. And what I'm going to do is take the acceleration at the next time step and the speed at the next time step equations that I just developed and plug them in. So here's my equation. Plug in the acceleration that I just developed, and I plug in the speed that I just developed on the prior slide. Now I simply need to rearrange terms so that I can get everything associated with n+1, or all the displacements with n+1 on the left side, everything else on the right hand side. First thing, I multiply the m and the c through everything, and then secondly, I gather terms. So on the left-hand side here, I've got the mass and damping and stiffness terms all multiplied by my displacement at my next time step. On the right-hand side, I've got the current time step displacement, the current time step speed, and the current time step acceleration, in addition to the force for the next time step. So that's the one piece that is considered known for my next time step. I know this is a lot of equations, but we are nearly there. So the expression I just have was for a single degree of freedom. For multiple degrees of freedom, I'm simply replacing the m, c, and k terms with m, c, and k matrices, and all of my degree of freedom, speed, and acceleration terms are now vectors. So the expression becomes this. This would be the FE form of that implicit time integration formula. So what we're going to do is rewrite this in a form that looks more familiar for a static analysis. So I've got k bar times dn plus 1 is going to be equal to F effective. And F effective is everything over on the right-hand side. So k bar is the left-hand side multiplier of dn plus 1. The F effective is, again, everything over to the right-hand side. And now, in order to use this term, I still need, because on the right-hand side I need the speed and the acceleration, I still need to find those in terms of my degrees of freedom and information from the prior time step. So I need an expression for speed and I need an expression for acceleration in the current time step based on the current and prior information. Lastly, in order to run this, I actually need some initial conditions. I need to know what my current speed is, my current acceleration, and my current position. But that's all the information you need then to start moving forward in time. And what you do is you analyze that k bar times dn plus 1 equals F effective equation at every time step. So it's sort of like you're doing a static analysis at every single one of your time steps. So let's take a look at how this works for a simple example. Again, we'll go back to 1 degree of freedom. So I have a mass that is connected by a spring and a dash pot or a damper to a rigid surface, call it a ceiling. And I'm going to define the displacement downward as positive, and it's in a gravity field. So I have gravitational acceleration. That's going to be my forcing function. So the spring is initially unstretched. I'm going to release the mass, and I want to see what happens to that mass for the first 2 seconds. Now we can predict this using other equations, but let's use FEA to see what we get for a result. So again, this is the equation that we have for calculating the next time step. Let's use the average acceleration version. So again, that was beta equals to 1/4 and gamma equals 1/2. So the equation becomes this when I plug in gamma and beta, but also plug in m, k, c, and I haven't done g yet because that's my forcing function. So m, k, and c are put in here. Now let's choose a delta t. I'm going to choose a delta t of 0.2 seconds. So I'm going to need 10 time steps in order to get to my final 2-second result that I'm looking for. Plug in that value for delta t, and I get this expression for my equation. Put in the variables, the units for each one of those, because I've been tracking them but I haven't put them on the screen. We've got 2,500 newtons per meter times dn plus 1 is equal to the Fn plus 1, which again is the gravitational force. Then I've got 1,500 newtons per meter times dn plus 250 newton seconds per meter times dn dot plus 10 newton seconds squared per meter times dn double dot. So that's the formula that I'm going to need to solve at each time step for dn plus 1. So continuing that analysis, when we solve in FEA this problem, we want to invert the stiffness matrix. In this case, the stiffness, the k bar term, is just 2,500. So I just divide by that. But if this were FEA with multiple degrees of freedom, we would be solving a matrix equation at this point. So this is the expression that I want to then progress with. I also need my speed expression. So here's the speed at the current time step based on the current and prior information, where I've also plugged in the delta t term. And then here's the acceleration at my current time step based on information at my current and prior time step, again where I've plugged in the delta t and the gamma and the beta. Okay, so now using my formula, I want to move forward in time. So I've got information at t equal to 0. I know that it's at rest and it's at position d equals 0, and I know that the current acceleration is the gravitational acceleration, 9.81 meters per second squared. So those are my initial conditions. So I can move forward, and I calculate then that the displacement at my first time step, so t equals 0.2 seconds, is going to be equal to 0.078 meters. Once I have that information, I can calculate my speed at this time step. So my prior speed, the dn minus 1 term, was 0 because it was at rest initially, plus 10 times the 0.078 minus 0 because my prior position was also 0. So that gives me 0.78 meters per second. Similarly for the acceleration, I've got 100 times the current displacement, 0.078, minus the prior displacement, which was 0, then minus the 0.2 times the prior speed, which was also 0, and then subtract out the prior acceleration, which was the 9.81. That gives me minus 1.96 meters per second squared for my acceleration. Now I can go to the next time step. So that's going to be 0.4 seconds. So d2 is, again, the 1 over 2500 times each of those terms, where now I've got the 0.078 and the 0.78 displacement and speed from the prior time step and the negative 1.96 acceleration from the prior time step. It gives me 0.157 meters for my deflection. My speed at this next time step is going to come out to 0, interestingly enough. So it's actually reached rest because of the reaction of the spring. And then my acceleration term becomes minus 5.89 meters per second squared, and so on. So this is the process to continue through and get yourself up to the 2 seconds. I haven't gone through the details of the rest of the analysis, but I do want to show you the final result. So here's what it looks like. This is the acceleration, or rather the position that we predict for this case, and it looks pretty good. So the implicit appears to be working. The accuracy might go up slightly if we go to a smaller time step. But that's the basic process for implicit analysis of a dynamic system.